Hello! Welcome to another one of my video log recording sessions. Water is good. Okay, I was thirsty. Welcome again to one of my sessions where I talk about genetic algorithms, basic beginner stuff, and maybe, if I'm smart enough, capable, onto advanced stuff. So today I'm going to talk about distributions, and today the date is 2025. Well, the year is 2025, March 30th, and today I am going to be very ambitious and try to cover seven Jupyter Notebook files, namely general genetic algorithm, grid search normal, grid search log normal, grid search uniform, grid search exponential as an exponent, or exponent as an exponential, and grid search von Mises, or is it von Mises or von Mises? I don't really know. This is the fifth one. The sixth one is general genetic algorithm grid search Pareto 0 dash and then general genetic algorithm grid search Weibull or Rebel. I don't exactly know how to read that. I heard Weibull, so Weibull 0. But before I start, I think it's worth the time to do a quick recap of my very previous video, and start dealing with what I intend to cover today. So, in my very last video, I had two occasions where I had the utility values and constraints values either sampled altogether from from either a normal distribution or a log normal distribution separately. But if one of them was sampled from a normal distribution, the other one would also be sampled from a normal distribution, or the other way around. So both of them would be from the same distribution, except that they'd be sampled separately. So that they would be different values, but yet still from the same distribution, given the same parameters. But anyway, and what I did then in my last video was set the maximum constraint percentage according to the total sum of constraint values, either to 0.5, 0-5, or 0.7, or 0-7, so that the maximum constraint value would be computed by multiplying the total sum of constraint values by the maximum constraint percentage. So if it was 50%, and if the total sum constraint value was 3000, the max constraint value would be 1500. Or if it was 0.7 or 70%, it would be 2100, and so on. And by doing that, I got and then what I did next was carry out the evolution, supposing that I was given only 10 genes, or 10 items, or 10 elements, and then 20 elements, and then 30 elements, and then 40 elements, and then see how the dip size percentage increased or decreased. And at the end of that video, I thought maybe I would just need to do a full scan over the whole spectrum, where the max constraint percentage starts from 0 and or 0%, and all the way up to 1 or 100%, meaning that the max constraint would be, given that the total sum of constraint values is, for example, 3000 again. If the max constraint percentage was set to 0%, the max constraint would be at 0, and if it was at 40, it would be at 1200. If it was at 50 or 0.5, 50% or 0.5, it would be at 1500, and if it was at 90, it would be at 2700, and so on. So all the way from 0 to 1.0. And the step in between would be 0.05 or 5%. So yeah, in total there would be what 20 or so. Is it 20? Oh, yeah, I could be wrong, but about 20 times, and do the whole search. So that's what these 7 files are going to be about. So if I wanted to make that clearer, I would have a utility value, util_vals. No. I would have n number of items. Let's just do this. Or this. I think this is better to... Yeah, this is better. And then if I had n items, so I would generate... if I generated n items from item 1 to item n, and then I would need to generate n utility values. And then I would also need to generate n constraint CST_RNT values, right? But and then yeah, this doesn't matter because it's just going to be named item 0, item 1 to all the way to item n. So this doesn't have a distribution. It just has an order, but the order or the number that comes after the word item underscore something doesn't mean anything. So this one doesn't have a distribution. However, this set of values for the utility values, for what we are going to use as utility values, would be sampled from, for example, a normal distribution. And if this, for example, if it was 10 items, the utility values, the 10 utility values would be sampled from here, for 10 times. And then when that is done, we have this set of values to be used as constraint values, and then we are going to sample it from another distribution, another normal distribution. Doesn't matter if it's the same distribution as this one, but we're just going to sample it 10 different times again. And then so that we would have 10 utility values and 10 constraint values. Yeah, and if everything were to be from a log normal distribution, for example, it would just be sampled from here somewhere for 10 times or 20 times or 40 times or 100 times. So that's it. And then what we do here in this notebook is, well, what I did to be exact. There we go. Nope, not here. Where is it? Don't tell me all the pictures here. I hope the pictures are here. Yeah, they're here. So what I did here is yeah, so, and the max constraint, that was so bad, I'm just going to type it. So the max CST RNT percentage list is going to should I try again? Max CST RNT per list is going to start from 0.05, 0.1, 0.15, and all the way to 0.95 and 1.0. So there are 20 values. There are 20 values that can each be a max constraint percentage. And we are going to iterate through all of that while we have 10 items, 40 items, and 100 items. Okay? And for each of the notebook file, I made the distribution that I used for both the utility values and the constraint values different. So what I did was for file for the file that has a word normal in it, I used the normal distribution for both set of values. For the file that has log normal, I used the log normal distribution. For the file that has the name uniform in it, I used the uniform distribution. So that's it. But I'm going to show show how or what the distributions look like right about now. So, and then yeah, for the 20 max constraint percentage values. It could have been a spoiler, but doesn't really matter because there's so much to see. So here we go. Here's the function as usual for the function to generate utility values and function. Well, it's the same function. Function to generate some values from a given distribution or from a claimed distribution, whatever. I think it's von Mises. I forgot the S there. I didn't know. How dumb of me. Anyway, so here are just some pictures of plots of what the distributions look like. This is the normal distribution when we have 100,000 items. Again, a bell curve, looking very normal, given some parameters. And this is what the log normal distribution would look like. Yeah, it looks a lot like a Burj Khalifa. And this is what the uniform distribution would actually look like. So quite uniform. This is what the expovariate or exponential distribution would look like. Quite similar to the log normal, but the difference is in how thin or thick this is. This looks like a skyscraper, whereas this looks like a very steep mountain. Well, again, that would also change depending on what parameters I give it, but right now it is what it is for now. I've just set it to some random or rather arbitrary values. This is what the von Mises, there should be an S there, but it's a typo or something, purely out of ignorance on my part. But anyway, this is what the von Mises distribution looks like when 100,000 items are sampled. This is what the Pareto distribution looks like. Again, very much like a huge, enormously tall skyscraper. That would look almost impossible. And this is what the Weibull distribution would look like. So kind of like this, but it doesn't. The highest isn't at the 0 or around 0. It's actually somewhere between 0 and 1. So that's about it. But I'll be coming back to how these look like per notebook. So the first notebook, I'll quickly go over what I did again using MS Paint. I generate 10 items, and then I set the utility values, meaning I generate 10 items, then I set utility values by sampling it from a normal distribution, but in this case, when I use the normal distribution, because all the values are centered around 0, I cannot have values below 0, because then it would very much mess up my calculation when it comes to the selector function and things like that. All the values being added have to be above 0. So I needed to, instead of this, I needed to, if this is 0 and this is where the distribution used to be, I need to shift it by some value, in this case shift it by 100 and have the value over here, so that all the values would be above 0. No, not that. No, above 0, something like that, so that the selector function would actually work. So, and so here is that's what I did, and then we go all the way down and then collect and store all the values necessary. Yep. Yeah, such as all result list head, the average of top 10%, and all the tails, or the bottom entity, the head being the top entity. And then the max constraint percent list is, it starts from 0.05 to 0.1, and then all the way to 1.0, like this. So there are 20 items, and then I loop through all of them. So for the first one, which is max constraint percentage, is at 0.05 or 5%, the max constraint is at 49.97 something, and I iterate for 5 times, and then store all the values so that I can do something with it, and then I set it to find out the average peak and the average plateau, and the average dip percentage and the average dip list, average dip sizes and average dip percentages. And then here's what the plot looks like. So this is only when there are 10 items, and the percentage actually rises a huge amount when the dip percentage when the max constraint percentage is at 1. It skyrockets when it's at 0.8. So because there's no context for now, let's just suppose we have no context. Let's just move on. Let's just say, wow, that's okay, surprising. Let's just move on. And then moving on. And then we have 40 items, so we generate from item 1 to item 40, we generate the utility values, and we generate the constraint values, and then we iterate again. We go through the loop, sequence evolution. So again, if the maximum constraint percentage is at 5% or 0.05, the max constraint is 200. When it's at 60%, it's at 2400.13 something. So when all that is done, we look at the graph again, and here we see that with 40 items, what happened, which is that when the maximum percentage is at 1, the dip percentage was at its highest. But however, now that we have more items or more space, for instance, and therefore a higher maximum constraint, things change. So the dip size or dip size percentage is the highest at around 0.8 or 80%, and then it starts coming down, and then it is as low as 0.02, or rather, what does it say here? Yeah, 1.9%. But this is also like kind of meaningless in a way, because if you set the maximum constraint percentage at 1, which means that you can just take everything. You don't really need to take the average of top 10% entities. There's no actual plateau, because you can actually take everything. So it's kind of meaningless, but it's cool to see that it goes up and down, as opposed to this one, where it just goes up and slightly down and all the way up when only 10 items are being considered. So with 100 items, we generate 100 items from item 1 to item 100, set the utility values, set the constraint values, and on we go along Z. And what happens is this part. Almost the same, very similar to what we saw when we had 40 items, right? And the dip size, average dip size percentage, average dip percentage falls, is at the highest when it's at 0.7 or 70% of the max constraint, of the total summed constraint values, and then it comes down when it's at 0.75, and then it just stays there. Slightly goes is lower, but it stays there. So this is when the utility values and the constraint values were sampled from were both sampled from normal distribution. Now let's check. Let's do it with log normal distributions. Now, what does a log normal distribution look like? Like this, a skyscraper, or one half of a Burj Khalifa. Of course, this is when 100,000 items are sampled, but that's what it looks like. Keeping that in mind, let's look at what we get when we have 10 items. Okay, kind of similar. It goes up. The dip percentage also goes up, and the dip size also goes up. Average dip size also goes up. The average dip percentage goes up. Let's look at 40 items. This is the plot for the average dip percentage, and it goes up, and kind of staggers, and then goes up again, and then it falls down. It is at its highest when we do, at around 0.8, or at 80%. Let's look at 100 items. Very similar. It's like you could not tell the difference apart. Yep, can't tell the difference. Nope, I don't think so. Are they the same? I could have actually messed up, and no, they're not the same, because I can see the difference here and here. Anyway, they look almost the same, and the maximum average dip percentage is 13%. And in a few of my previous videos, I've said that if the dip percentage is below 3 or around 3% or less, I would just consider it as no dip. But right now, there we go, 0.6, and so dips start happening when the maximum constraint percentage is 0.55 or 55% or above, and then dips don't occur, we could say, when the maximum constraint percentage is 85% or above. Yeah. And it is at its highest when it's at 0.75 or 75%. When log normal distribution is used both for the utility values and the constraint values. And next up is when we sample both separately from a uniform distribution. So to clear that up again, we sample this, go away. We sample this from a uniform distribution, we sample this from a uniform distribution, but they're not the same. They're not necessarily the same. They could be, but that's a very low chance, so they're not the same. And okay, 10 items. When we are only dealing with 10 items, this is what happens. So we've seen that. When we are dealing with 40 items, this is what happens. Again, we've seen this. It goes up and it comes down. And when we deal with 100 items, this is what happens. So again, the maximum average dip percentage occurs at 0.75 or 75% of the total sum of constraint values, and they come back down when it's at 0.8 or 80%. And the maximum average dip percentage was 0.13 or 13% when we use the uniform distribution. So what if when we use a exponential distribution? What then? So this is what an exponential distribution would actually look like. Then again, the two sets of values are sampled differently and separately from the same distribution. And here are the results. This is when we have 10 items, so it's still going up until the 100% mark. The 40 items, when it goes up and then comes down. And here are the here's when we have 100 items. It goes up a bit earlier and then it drops drastically downwards and then just stays there at around the 0.75 mark. Yep. So starting to see a pattern here. And of course all the distributions at the end of the last iteration so far kind of look like a normal distribution if you look closely. So this is when we had 100 items, and this is what the final distribution looked like. I don't have that. Okay, that's bad. Oh, I don't have that here either. That's bad. I missed it. Oh, here we go. Normal distribution when we're using uniform. And exponential, a normal distribution. Next up is the von Mises distribution. So what does a von Mises distribution look like? It looks like this, like a valley, like a rift or a valley. And what does this strange distribution do to our experiment? Shall we see? So this is when we have 10 items, almost the same. This is when we have 40 items, a bit wider, a bit thicker, this graph, but then again we do reach some kind of a top at around the 0.8 or 80% mark, and then we come back down. So as expected. So far the only difference is when the average dip percentage is at its highest. Is it at 0.65, or is it at 0.7, or 0.75, or 0.8, or rather 60%, 70%, or 80% of the max constraint of the 60%, 70%, or 80% of the total constraint sum, or total sum of constraint values rather. And this is when we have 100 items. Again, we have the highest at 0.75, and then we are back down to 0.8, and we stay there, and they're all below 0.03, and the highest average dip percentage was at 17%. So the highest so far. Yeah, so the highest so far. And now we're going to use the Pareto distribution, which looks like this. Yep. Pareto distribution, and this is when we have 10 items. Again, the trend just keeps going up. The trend dictates that the plot just keeps going off. Yeah, all the red ones are the actual average dip sizes, and the blue lines are the average dip percentage. So they look similar, but they're not exactly the same. And if plotted on the same, on the same scale, this one would just look really minuscule and wouldn't actually show. So, which is why I keep it in a separate plot. I could do it like 1 by 2 or 2 by 1, but I couldn't be bothered. So I'm so lazy. And this is when we have 40 items. Again, very similar. It goes up and then comes down at around the 0.8 or 0.75 mark, 75% or 80% mark, and then and then when we have 100 items, again the same. And here I had the willpower to draw a horizontal line at 0.03, which is the 3% mark, which means that dips started happening when the max constraint percentage was at 0.6 or above, until we came all the way down to, it only happened 3 times, and then when the max constraint percentage was at 0.75 or 75%, we kind of stopped having dips. And the highest average dip percentage was at 0.09 or 9%. But one interesting thing here that I should mention is that when I looked at the distribution of the last iteration of the final evolution, or the last iteration of the final evolution, or the final evolution of the last iteration, whatever, this doesn't look so normal. It looks more like a bimodal distribution. Is that the right word? Bimodal? Bimodal. Yeah, 2 peaks. So it looks like a bimodal distribution when I use the Pareto, which is odd. I don't know why. Which would eventually lead me to my next set of experiments. But anyway, this is how it is for now. Again, same trend, goes up and then comes down, as expected. And the question was when it would be at its highest. And the last notebook, but not the least, is when I use the Weibull distribution to sample both the utility values and the constraint values, but separately from the distribution. And when I only have 10 items, this is what it looks like. Again, the same. What does a Weibull distribution look like, if you might ask? This is what it looks like. when you have 100,000 items, this is what it looks like. So at 0 it's not the highest, but there's a fair bit of amount. There's still a lot, but it is the highest. There are, yeah, this plot is at its highest. This histogram is at its highest when the value is at around 0.5 or 0.4, and then it comes back down when given the parameters that I'm using, where the alpha is at 1 and beta is at 1.5. So anyway, this is when I have 10 items. This is when I have 40 items. Again, very same. But see, we come down a bit later. And then this is when we have 100 items. Again, the maximum percentage, the average dip percentage is at, is back at its lowest after 0.75. So the peak is at 0.75 when it comes to the maximum constraint percentage, and the dips don't happen until 0.4, 0.5, 0.55. Dips kind of start happening when the maximum constraint percentage is at 0.55 or 55% or above, until it goes all the way down, all the way up to 0.8. That's when the average dip percentage or the average dip sizes just plummet down again to the point where you can't say that dips exist. And the maximum average dip percentage was at 0.146 or 14.67%. 68, if you round this up. Yeah, that's about it. So regardless of what distribution you use, you will get dips, or you'll start having dips when the maximum constraint percentage is close to or slightly above, or starting from around 0.5 or 0.55, or mostly 0.6, and when the maximum constraint percentage is around 0.7 or 0.75, you will have the biggest average dip percentage, or the biggest dip sizes. But past that point, your dip sizes plummet down, and then there are no dips anymore. So yeah, that's depending on what distribution you use for both the what same distribution you use for both the utility values and the constraint values, you will have dips at around the 0.7 mark in terms of max constraint percentage. However, there will be some differences as to the size of these dips, or the size of these average dip percentages. And in maybe in a few cases, maybe more than one, you will have a different looking distribution of entities in terms of their summed utility values. You will most likely have a unimodal distribution, but for example, when the Pareto distribution is used, you might end up with a bimodal distribution. So that's that. But however, next up, I wanted to find out what would happen if I sampled these separately from different distributions. For example, I could sample the utility values from a normal distribution, and then I could sample this from an exponential distribution, or I could sample utility values from the variable distribution, and then I could sample the constraint values from Pareto, and then see if what I found out today would still hold. But then I decided that that's also another video. I need one more video before I do that, which is which would deal with the difference in the order of things, or how I do things when it comes to sampling and then running the evolution. So right now, what I do is I generate the number of items. I generate the items. Oh, what did I do? Wow, god damn it. I generate, for example, 20 items. Well, let's just say 40 items. And then I generate 40 utility values, and then 40 constraint values, and then run, for example, 5 times. Run the evolution 5 times while these are fixed. I mean, this does have, would serve some kind of a purpose, but would it mean more, or would it mean something? Would it lead to different results if I sampled, if I just have a number of items just fixed, some items, just suppose that I needed 20 items again, or again, let's just say 40 items, and then I wanted to evolve 5 times for 500 generations, for example, for 1,000 entities, and then evolve it for 5 times. So that's 500 generations times 5. That's 2,500 generations in total. But per evolution iteration, so iteration number 1, I generate the 40 items, and then I generate these new utility values and new constraint values, and then carry on with the evolution. And then once that is done, for the second iteration, I get rid of these and then get new values, and then carry on with the second iteration of the evolution for 1,000 entities for 500 generations. And then the third, again, same, get rid of these, and then bring these on, and maybe and do it for 5 times, 4 and then 5. Maybe I need to do this, and then find out if the results from this method is the same as what I did today and yesterday. And once that is all cleared up, once this is cleared, and once this is cleared, that's a horrible way of doing it. Once these are cleared, I could move on to this. I could, take what I can from what I've learned here, from both of these occasions, and then move on to sampling from different distributions for the 2 sets of values. And then when I do have 2 sets of values, there are 7 distributions so far, 7 dists so far, and I could have, so therefore there would be 7 times 6 ways of doing this, 42. Because it's either going to be normal for utility values and exponential for utility values, and then it could be exponential for utility values and then normal for constraint values. So there are 72 ways of doing this. And then each script for now, for this one, for example, this took me about 100 minutes. With some leeway and some adjustment, it took about 100 minutes. So 42 times 100 is 4200. Divide that by 60 is 70. So that's 70 hours. Why am I doing a percentage? So that's 70 hours, which is approximately 3 days. That's a long ass time to compute. That's way too long to compute. So I either need to find a better way to bypass some of the challenges and obstacles to shorten this, or I could just brute force everything. Sometimes just going along with it and brute forcing solves the problem rather than trying to minimize it. I just need to focus on the right thing right now. So that's the plan for now. Well, thanks for watching. It's 46 minutes and counting. That was a long video. Yeah, thank you again. Goodbye.